Hello everyone, so today in this video we're going to talk about what exactly is the first law of thermodynamics. So first, to understand what the law is, we need to know what is a system, a surrounding, and a boundary. So we're going to start with this. A system is what contains devices and matter and is really the focus of our study. The boundary, on the other hand, is what is denoted by a dashed line and is what separates the system from the surrounding. During our study, we're really going to focus on what goes through the boundary, so what goes out and what comes in. Knowing this, we can now talk about the different types of systems. There's three main types of systems. There's controlled mass, controlled volume, and isolated systems. Controlled mass are defined by a system that don't allow any mass exchange between the system and the surrounding, but they allow energy exchange in the form of heat and work. On the other hand, isolated systems are systems that don't allow any interaction whatsoever between the system and the surrounding. And finally, there's controlled volume systems, which allow mass exchange between the system and the surrounding, and also energy exchange between the system and the surrounding. It's on controlled volumes that we're going to concentrate on.
So we're going to talk about the formula of the first law of thermodynamics. As we know, energy cannot be created and destroyed. It can only be transformed. So in a system, the energy flowing in and flowing out must be equal because of the energy in the system must be constant. So what is energy? We can define specific energy by the specific internal energy plus the kinetic energy plus the potential energy. The kinetic energy is the velocity squared over 2, and the potential energy is the constant gravitational times the height with respect to your reference point. So now that we know all these aspects, let's talk about what is really the equation of the first law of thermodynamics for controlled volumes. Like I said earlier, the energy flowing in the system is equal to the energy flowing out. And also define the specific energy like this equation. We also need to consider that the mass does the work flowing in and flowing out, and this workflow is equal to PV times the mass flow. Putting in those together, we have this equation, and we can see that U plus PV appears, and we already know that those together equal to the enthalpy. We also know that we are in a steady state process and that the energy flowing in the system and out the system is constant and doesn't vary with time, so this term is equal to 0. It is a steady state process, so we can put the mass flow rate times the energy flowing out the other side so they can be equal. And now we have the equation of the first law of thermodynamics for a controlled volume at a steady state process. And we also need to consider the work and the heat. We don't always have one inlet and one outlet for in our systems, and we need to consider all of them. So that's why we put a summation term here.
The first law of thermodynamics can be simplified, where for a steady state, the total amount present at any instant remains constant. Also, the heat transfer between the fluid and the surface of the nozzle or diffuser is neglectable, and there's no change in height, which means that the potential energy can be dropped out, and there is no work done by any rotating shafts, displacements of the boundary, electrical effects, or other work mechanisms associated with the controlled volume being considered. So that leaves us with that equation. A simple example of nozzle is steam entering a nozzle with a 600 kilopascal pressure, a 200 degree Celsius temperature, and a 50 meter per second velocity, where we can find the initial enthalpy with a superheated table. And with that equation and the velocity at state 2, we can find the enthalpy at the exit. It is also possible to find any other property that is in the table for state 2, like specific volume, and that is it for nozzle and diffuser.